Hi Year 9 students, I'm Norman Wahlberger. In our last video we are reviewing fractions. Today we're going to continue with that. We're going to talk about the arithmetic with fractions. Very important subject for Year 9 students to have mastered. The reason for why fractions are so important and the arithmetic with fractions is so important is because it's the basis of algebra that we're going to be starting on this year. Okay, so we're going to start with addition and subtraction of fractions, which is in fact a little bit harder than multiplication and division in some respects. So let's remind you that here is our number line. So we're going to think about numbers as being points on the number line. And here are our integers. And we saw last time also that we could talk about fractions as being sort of intermediate between these integer values. And here I've shown you multiples of 1/5. So I've divided the interval from 0 to 1 into 5 equal pieces with these intermediate lines. Okay, you can see there's 1, 2, 3, 4, 5 subintervals, evenly divided. And I've done the same thing for all of the other intervals. And so we give this particular marker here the name 1/5 because it's 1/5 of the whole interval. Once that's 1/5, then the next one is 2/5. It's this one plus this one. And then the next one is 3/5, 4/5, 5/5, and so on. We could keep going, 6/5, 7/5, 8/5, 9/5, 10/5, 11/5, 12/5, and so on. Alright, so every point that we've got marked here is a multiple of 1/5, so it's actually of the form n over 5 for some integer n. So doing arithmetic, at least the arithmetic with addition and subtraction, is easy with just those kinds of fractions. So if we restrict ourselves to just, say, multiples of 1/5, then arithmetic is pretty easy. So for example, 3/5 plus 4/5. So we're adding this length to this length. 3/5 plus 4/5 is 7/5. You can think of that as here's 3/5, and then if we go another 4/5, 1, 2, 3, 4, we end up there, which is 5, 6, 7/5. 4 times 3/5 means 4 copies of 3/5. So there's 3/5, and I want 4 copies of it. Well, there's 1, 2, 3, 4. We end up with 12/5. Similarly, 6/5 plus 8/5 is 14/5. 18/5 minus 3/5 is 15/5, and 15/5 is the same as 3. There's 5, 10, 15/5 is right here. So we can get the simpler name by dividing the common factor of 5 from the numerator and the denominator, giving us just 3 over 1, which is the same as 3. We also can multiply by negative numbers. So I remind you, when we multiply by -1, we change the sign of the number. So -1 times 4/5 will be minus 4/5. There's 4/5, there's minus 4/5. Or a little bit more fancy, if we multiply by -3, then it's the same thing as multiplying by 3, so we get 21/5, and then multiplying by -1. We can also work with mixed fractions. So for example, 4 and 1/5 plus 2 and 3/5. Where are those numbers? So here's 4 and 1/5 will be right there. And 2 and 3/5 will be right there. So we want to add 4 and 1/5 to 2 and 3/5. And one way of doing it, which is quite effective in this case, is to add the integer parts. So add the 4 and the 2 together to get 6, and add the 1/5 and the 3/5 together to get 4/5. Another way would be to convert both of them into composite fractions, to write 4 and 1/5 as 21/5, because the 4 is really 20/5. 5, 10, 15, 20, and if we have one more, well, then we have 21/5. And this would actually be, let's see, 2 is actually 10/5, so it would be 13/5. So we can also calculate it that way, 21/5 plus 13/5, which I suppose is 34/5, which is another way of writing that. 7 times 2 and 4/5. Well, that's the same as 7 times 14 over 5. So the 2 and 4/5 is the same as 14 over 5 because 2 is the same as 10/5. So whereas 2 and 4/5, it's right there. It's really 10, 11, 12, 13, 14/5. And when we multiply that by 7, we have to multiply the 14 by 7 to get 98 5ths. And if we wanted to, we could convert that into a mixed fraction by dividing the 98 by 5 to give us 19. And then there would be a remainder of 3, so it would be 19 3/5. So we could leave it either in this form or in this form. So these are examples of arithmetic with fractions where the denominator is always the same. In this case, always 1/5. And exactly the same kind of reasonings work when we're working with fractions whose denominators are always 1/3 or 1/7 or 1/23 or something like that. If the denominators are always the same, then the arithmetic is really very much just like integer arithmetic. Alright, so let me remind you that when we're doing mathematics, when we're learning mathematics, it's important to practice as well as to listen and to absorb and to read. So here's some practice problems, relatively simple ones I hope, that just give you some practice in calculating with fractions whose denominators are all the same. Alright, so the first problem is to calculate these various quantities. And notice here it's a little bit more complicated. I have 8 times 4/13 plus 3 times 1/13. Okay. So I haven't put brackets around here, but I hope you remember that when you have combinations of multiplications and additions, that the convention is that you do the multiplications first. So this means you have to multiply 8 times 4/13 first, and then you have to add to that the result of multiplying 3 times 1/13. So I could also have put brackets around these two and brackets around these two, making it clearer what order to do things in, but it's important to learn what the right convention is, that you don't actually need the brackets there. Okay, and here are some more, maybe a little bit more complicated with some mixed fractions and so on. And I've given you the answers, but not in the right order. Okay, so you can check if you've got an answer. You can look to see if your answer is in the list somewhere. Hopefully I haven't made a mistake. If I've made a mistake, let me know. So considerably more tricky is the question of how do we add or subtract fractions with different denominators. It's not quite like adding apples and oranges. The trick is to convert them both to equivalent fractions with the same denominator. This is the strategy. So let's have a look with 1/2 plus 1/3. They don't have the same denominator. So we can't say it's 2 somethings. It's definitely not 2/5. Okay, definitely not. But what we're going to do is convert each of them into a fraction whose denominator is 6. And we can do that with 1/2 by multiplying the top and the bottom by 3. Remember that when we multiply the top and the bottom, in other words the numerator and denominator, by the same number, then the fraction doesn't change. We get what's called an equivalent fraction. So 3/6 is the same as 1/2. And similarly 2/6 is the same as 1/3. Why is that? Because we've multiplied top and bottom here by 2 to get 2/6. Now we are in a position of having 2 fractions with the same denominator, so now we know what to do. 3/6 plus 2/6 is 5/6, and so that's the answer. How about a subtraction? 3/4 minus 1/3. The denominators are different, so we're going to rewrite them both as equivalent fractions with a common denominator of 12, as it turns out. And perhaps you can guess why we're going to use 12, because 12 is 4 times 3. So that means that we can multiply top and bottom of this fraction by 3, giving us 9/12. And we can multiply top and bottom of this fraction by 4, giving us 4 over 12. So this is equal to 9/12 minus 4 over 12, which is 5 over 12. Once we get the same denominator with both fractions, then the subtraction is just the subtraction of the numerators, just like in the previous slides. 2 over 7 plus 1 over quarter. We're going to use the common denominator of 28, which is the product of 7 and 4. That will work because then we multiply top and bottom of this by 4, and we multiply top and bottom of this by 7, giving us 8 28ths plus 7 28ths, for a total of 15 over 28. Here, with this fraction having a denominator of 9, this one has a denominator of 5, so we're going to use 45, the product of these two, as the common denominator. So we're going to multiply top and bottom of this fraction by 5, changing it to 35 over 45. We're going to change the top and bottom of this one by multiplying by 9 to give 27 over 45. And then we do the subtraction. 35 minus 27 equals 8 over 45. So you can see that some multiplication is involved here. And I hope you can see that it's really important to have the multiplication table down so that you don't have to rely on a calculator to make this kind of computation. So we're going to make the computation 7 times 5 is 35, and we're going to ultimately multiply 9 times 3 to get 27. You want to just be able to write these things down without having to go to a calculator and calculate it. Right? So very, very important to memorize the multiplication table. Alright, so in each of these cases, the common denominator that we used is the product of the denominators. So this is a surefire method that always works, but sometimes a simpler method also exists that I want to tell you about. So this will always work, but sometimes there's a simpler method, a simpler denominator, not quite so big, that we can use. So here's some examples of simpler denominators working, where we don't just multiply the two denominators that we have. So let's have a look at this one. 1/2 plus 3/4. We can rewrite both these fractions in the following way. We can rewrite 1/2 as 2 over 4, just multiplying by 2. And we can leave this one where it is, 3 over 4. That one operation now has the denominators being the same. So we can just add them in the standard way. 2/4 plus 3/4 is 5/4. Here's another example. 5 over 3 minus 1 over 12. Now we're going to use 12 as the common denominator. So we only need to multiply this fraction top and bottom by 4. 20 over 12. We can leave this one where it is, minus 1/12, give us then altogether 19 over 12. So in these cases, what we did is we saw that one of the denominators divided the other denominator. Or another way of putting it, one denominator was a multiple of the other one. 12 was a multiple of 3. So to get a common denominator, we can use that bigger denominator that's already a multiple of the other one. Hope that makes sense to you. Okay, so here's a little bit more sophisticated version of that kind of thinking. Here we have a denominator of 6 and another denominator of 9. Okay, so the product of 6 and 9 would be 54. So we could use 54 as a common denominator. We could multiply top and bottom here by 9 and multiply top and bottom here by 6. But there's a simpler denominator that we can use. All what we really need is a number which is a multiple of both of them. So can we think of a number that's smaller than 54, which is also a multiple of 6 and a multiple of 9? Well, multiples of 6 include 18, and the multiples of 9 also include 18. So 18 works. 18 is a multiple of 6, and it's also a multiple of 9. So the idea is to convert both fractions to fractions that have denominators 18. How do we do that? How do we convert this fraction into a fraction with denominator 18? We have to multiply top and bottom by 3, right? So we multiply 6 times 3, that's 18. 5 times 3 is 15. To convert this one, we're going to have to multiply top and bottom by 2. 9 times 2 is 18. And then 4 times 2 will be 8. So we've converted both of those fractions into equivalent fractions, now with the same denominators. And then adding them is simple. We just add the numerators. 15 plus 8 is 23. So we get 23 over 18. Here's another example. A denominator of 15, a denominator of 9. We're subtracting those fractions. We don't particularly want to use the product because it's getting to be a little bit of a big number. 15 times 9. So we think, well, is there some smaller number which is a multiple of this one and a multiple of this one? Okay, so maybe some thinking is involved here. 45 is a multiple of 15. In fact, it's 3 times 15. And 45 is also a multiple of 9. It's 5 times 9. So we can convert 1 over 15 to 3 over 45 by multiplying top and bottom by 3. And we can convert 4 over 9 to 20 over 45 by multiplying top and bottom by 5. Now we have 3 over 45 minus 20 over 45. Then we only have to worry about the numerators. 3 minus 20 is, well, we get a negative number in this case, but that doesn't bother us. Minus 17 over 45. Alright, so here's some practice problems for you to do. Calculate the sums and differences, and here are the answers in some order or another. And in general, what we're doing here is the least common multiple. So the least common multiple is the simplest common denominator that we can use. It's the multiple of both of them, which is the smallest one. But if the theory of least common multiples is a little bit complicated for you, remember that you don't really have to worry about it. You can always just use the product of the denominators. And I think this is the way students should be taught at first. This is the default thing that you do. You just use the product of the denominators as the new denominator, the common denominator. You may have to be aware that at some point, if you do that, where you could have done one of these methods, then you may end up having to cancel something from the answer at the end. So let's think just for a second, what would have happened if we had used 2 times 4 is 8 as the common denominator here? What would have happened? We would have gotten 4 over 8 for this one, and 6 over 8 for this one. When we add, then we would get 10 over 8. So the 10 over 8 is correct, but it's not in the reduced form because we can divide a 2 from the 10 and from the 8. And if we do that, then we would get 5 over 4. So we can get the same answer, but we just have to be aware that when we make a calculation with fractions, we should have a look at the end to see if there's some common factors in the numerator and the denominator that we can cancel to simplify the fractions. So great, we've had a review of addition and subtraction of fractions. And now let me summarize for you the main formulas that cover all of the cases that we've talked about. And we're going to use a little bit of algebra here in formulating these formulas for you in a general way, not with particular numbers, but with general numbers, which we're going to use letters for. All right, so the general formula for the addition of two fractions, so here are two arbitrary fractions, a over b plus c over d. And you should think of a and b and c and d as some numbers that you just don't happen to know. They're mystery numbers. They're variable numbers. They're unknown numbers at this point. But they're numbers. They just happen to be represented here by these letters a, b, c, and d. So in terms of these letters, how do we add these things? Well, remember what we're going to do is we're going to look for a common denominator. What's the common denominator that we're going to use? It's the product, b times d. And I remind you that when we're talking about letters, we usually just put BD, not the times sign. So when I put BD together like that, it means the number B times the number D, whatever B and D happen to be. We want to multiply top and bottom by D. That will get the B into the form BD, and we'll take the A into the form AD. So A over B is the same as AD over BD. Similarly, if we want to take this abstract fraction, C over D, and convert it into one that has denominator BD, then what we're doing is we're multiplying top and bottom by B. Okay, if we're multiplying the denominator by B, we have to multiply the numerator by B as well, to getting BC over BD. Now at this stage, they have the same denominator, namely BD. And so we're just going to add this numerator to this numerator, whatever they are. And so we can write the result as AD plus BC over BD. And I've summarized that here for you. So A over B plus C over D equals AD plus BC over BD. That's a general rule that covers all cases of addition with fractions. Okay, and it's very important to understand this derivation and then to memorize it. Okay, but first we want to understand it and then we want to memorize it. So notice that it's giving us a pretty slick way of doing addition. It's telling us that if we have two fractions here, the numerator of the sum will be this number times this number, there's the AD, plus this number times this number. This times this, plus this times this, that's the numerator, over the product of the denominators. You can go back and check the examples that we did on the previous page and show that that's really exactly what we're doing. With subtraction, it's very much the same story, except that there's a minus sign instead of a plus sign. And there I've summarized that for you. That's a very important formula, but it's also an introduction to algebra, because we're really making manipulations with letters, thinking of the letters as just being placeholders for some particular numbers. It's just that we don't want to be specific about which numbers we're talking about. Sometimes we might want to talk about 3, and sometimes another time we're talking about 5 or 6 or 10 or 49. Working with the letters allows us to cover all of those cases at the same time with this one single formula. Alright, so let's turn our attention to multiplication. And remember, when you're watching these videos, you don't have to watch any one video all at once. You can watch half of the video, like the section that we've just done, take a pause, come back a day or two later, and watch the second half a little bit later. All right. And also, you can go back and watch the portions of the videos several times to make sure that you understand a particular segment. So I'm being pretty concise with these videos, probably more concise than you're used to as Year 9 students. So that means it's up to you to go over the material that you haven't understood, try to make sure you understand everything that I'm saying. So now we're going to have a look at multiplication involving fractions. Let's start off with a relatively simple example. What does 1/3 times 12 mean? Okay, what are we going to think when we see 1/3 times 12? Well, let's remind ourselves that when we have 3 times 12, we're going to think about that as meaning 3 groups of 12. 12 plus 12 plus 12, which is 36. So 1/3 times 12 should mean 1/3 group of 12. 1/3 of a group of 12. Not 3 groups of 12, but 1/3 of a group of 12, which is 4. So this makes sense because 1/3 times 12 really ought to be the same as 12 times 1/3. And we have already talked about what 12 times 1/3 is. It is 4. So here's our number line, and let's have a look at what we're talking about here. 12 is this whole interval up to here. Whoa, no, just up to there. And 1/3 times 12 means we want to take 1/3 of the group of that. Well, this is really dividing it by 3 in this case, which is 4. Because if we do another copy of that, get 8. Another copy is 12. So this also makes the associative law work. So if we interpret multiplication this way, it's consistent with the associative law. Have a look at this product here. 3 times 1/3 times 12. We've just been thinking about what this means. Okay? And we've decided that this ought to be 4. In which case 3 times this would be 3 times 4 or 12. But if the associative law holds, and we want the associative law to hold, then this should also be the same as this, where the brackets are now organized this way. 3 times 1/3 first, then multiplying by 12. And what is 3 times 1/3? Well, there's 1/3, there's 1/3. So 1/3 plus 1/3 plus 1/3, 3 times 1/3 is 1, of course. So this is just 1 times 12 or 12. So our interpretation of this as 4 is consistent because it makes then this product equals this product, which we want to have happen. Alright, so some other examples. 1/5 times 20 is 20, and we're taking 1/5 of 20. It's another way of saying it. We're going to get 4. It's really the same as dividing 20 by 5. How about 2/5 times 20? Well, if 1/5 times 20 is 4, then 2/5 times 20 should be 8. How about 2/5 times 15? Well, think about the 1/5 first. What's 1/5 times 15? We're talking about 1/5 of 15, which is 3. And so 2 times 3 would be 6. How about 1/2 times 4? Well, that's 2. 1/2 times 3? That's something new. Here, when we took 1/2 times 4, we're essentially dividing 4 by 2. When we multiply 1/2 times 3, we're essentially dividing 3 by 2. And so we're getting 3/2. So the result of multiplying a fraction by a number can be another fraction. Here's another example. 1/5 times 7 is 7 divided by 5, or 7/5, or 7 over 5. Alright, so that's how we multiply a fraction times a number. Okay, so let's extend that to multiplying two fractions. For example, 1/2 times 1/3. How should we think about that? Well, it should be 1/2 of 1/3. On our scale, our number line, which is where we like to think of everything happening, here's the interval 0 to 1. I've shown you 1/3 here and 2/3 here. So there's 1/3. What's 1/2 of 1/3? Well, if you take 1/2 of 1/3, you're getting that interval, half the size, which is 1/6. So if we divide the interval into 3, we get these 3 equal pieces. If we divide the interval into 6, we get 6 equal pieces. And 2 of the 6th make a third. Or another way of putting it, 1/2 of a third is a 6th. And so notice that at the level of the numerators and denominators, the numerators are multiplying here to give you the 1, and the denominators are multiplying here to give us the 6th. So here's some more examples of multiplying fractions. 1/3 times 2/5 equals 2/15. So 1/3 of 1/5 would be 1/15. 1/3 of 2/5 would be then 2/15. Again, we're multiplying the numerators and we're multiplying the denominators. 1/4 times 8/3 is 8/12. And now there's a bit of cancellation that can take place because the 8 and the 12 have a common factor of 4. So we divide the 4 out. We prefer to rewrite the 8 over 12 as 2 over 3. 2/3 times 1/2 is 2 over 6. Simplify by noticing that there's a common factor of 2 top and bottom. So cancel out those common factors to get 1/3. 3/4 times 1/5 is 3 over 20. And so the general rule is, in terms of our letters, A over B times C over D is A times C as the numerator over B times D in the denominator. And here are some practice examples of multiplication with fractions and some answers. While most students find multiplication of fractions pretty simple, division with fractions is usually a little bit trickier to understand. So let's start with a simple example. What does 3 divided by 1/2 mean? And I'll note that this notation and this notation are really the same. So 3 divided by 1/2, another way of writing that is 3 divided by 1/2. That horizontal line means divided by. Okay, so let me remind you that one meaning of, let's say something different, 42 divided by 3, or 42 divided by 3. One meaning of that is, how many 3's fit into 42? If I ask you what is 42 divided by 3, there are two possible interpretations. One is what happens when you divide 42 into 3 equal pieces. Another interpretation is how many 3's fit into 42. Let's look at this second interpretation. How many 3's fit into 42? Let's apply it to this situation. 3 divided by 1/2 is going to be 6, because we're asking how many halves fit into 3. And it turns out that 6 times 1/2 equals 3. So here's a way of visualizing it. Here's the number 3, and we're dividing by 1/2. Here's 1/2. So we're really asking how many halves fit into 3. Okay. If in this first question, 42 divided by 3, I would write the big interval 42, and I would ask how many 3's fit into 42. 1 3, 2 3, 3 3, 4 3, up to 14 3's. Okay, so let's do some other examples. 5 divided by 1/2, what would that be? Well, here is 5, and dividing it by 1/2 is we're essentially asking how many halves fit into 5. Well, we can almost do it here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 halves fit into 5. So 5 divided by 1/2 is 10. Let's do another one with the other notation for division with the horizontal line. So 5 divided by 1/4. What's that going to be? Well, on this picture here, where is 1/4? Here's 1/4 right here. Okay, 1/4 is 1/2 of 1/2. So asking what is 5 divided by 1/4 is asking how many 1/4's fit into a 5. Can you figure it out from this diagram? How many of these little segments, now only this long, how many of those fit into 5? Well, let's make it simpler by saying, well, 4 of them fit into there. So 4 of them there, another 4, another 4, another 4, another 4. Altogether, 5 times 4, 20. It's the same as 5 times 4, 20. Here's a little bit more sophisticated one. 5 halves divided by 1/2. Okay, where is 5 halves on the number line? Well, there's 1/2, 2 halves, 3 halves, 4 halves, 5 halves. There's 5 halves right there. Okay, so when I'm asking 5 halves divided by 1/2, one way of interpreting that is to say, well, how many halves fit into 5 halves? There's 1/2. How many halves fit into 5 halves? We can count them. 1, 2, 3, 4, 5. 5 of them. So 5 halves divided by a half is 5. How about minus 2 divided by a third? And probably I should put brackets around here to make sure there's no ambiguity. All right, let's do that. So minus 2 divided by a third, it's a lot like 2 divided by a third, except it's a minus involved. So minus 6 is the answer, because minus 6 times a third is minus 2. Here's another one involving fractions, but written with horizontal line. So 3 halves divided by a quarter. Where's 3 halves in the picture? There's half, 2 halves, 3 halves is right there. 3 halves divided by a quarter. How many quarters fit into 3 halves? So you can see it's quite useful to think in terms of a number line, because we can just think about adding little segments. Here's a quarter. We're asking how many quarters fit into 3 halves. Well, let's count them. 1, 2, 3, 4, 5, 6. So we can count 3 halves over 1 quarter is 6. Let's circle these ones. And something a little bit different, 5 halves over 1/3. A little bit trickier. There's 5 halves. Dividing it by 1/3 is asking how many thirds fit into 5 halves. Well, I haven't marked thirds here, but let's see if we can just roughly guess. Okay. There's 3 thirds that fit there. Another 3 thirds that would fit there. How many thirds fit into here? Well, if I divide this up into thirds. So how many thirds do we have altogether so far? We've got 3 of them there, and we've got 3 of them there, and we've got 1 of them there, and then you can see we have to have a half of a third. It's not a whole number of thirds that fit into 5 halves. It's 3 plus 3 plus 1 plus a half, so 7 1/2. And we can rewrite 7 1/2 as 15 over 2. Either of those answers is right. All right, so that's a visual introduction to division by fractions, but obviously we don't want to be drawing number lines and trying to subdivide when we actually want to make a calculation. I want you to think about the number line as an explanation of what's going on, but ultimately we want to be able to just take this expression and do something to it to get, well, either 15 over 2 or 7 1/2. So we also need an algebraic way, and fortunately there is a very simple algebraic way of dividing fractions. Okay, so the key idea to make division by fractions simpler is to introduce this idea of the reciprocal of a fraction. Okay, yeah, it's very simple. The reciprocal of a over b is b over a. We just interchange the numerator and the denominator to get what we call the reciprocal. Okay, so when I make a line like this underneath something, it means I'm defining, I'm explaining to you what I mean by the word reciprocal. Okay, and then a crucial property of the reciprocal is that if you take the original fraction, a over b, and you multiply by the reciprocal, b over a, then lo and behold, you get 1. So any fraction times its reciprocal is 1. Why is that? Well, because we know how to multiply fractions, right? A over b times b over a. We just multiply the numerators, which gives us a times b, and we multiply the denominators, which gives us b times a. And since a times b is the same as b times a, they both cancel and we get 1 over 1, or just 1. So this is the crucial property of the reciprocal, that the reciprocal is telling us what the inverse of a fraction is. It's the fraction that you have to multiply by to get 1. And so here's how we use the idea of reciprocal to simplify division by fractions. So let's consider this division. 3 over 4 divided by 7 over 5. Okay, so I'm going to multiply, there's the fraction itself. I'm going to multiply by 5 over 7 divided by 5 over 7. Where did 5 over 7 come from? Well, that was the reciprocal of the denominator. And this over this is going to be 1 because this is equal to this. So multiplying by 1 doesn't change whatever I have. That's why I'm entitled to say that this actually equals that, because I'm just multiplying by 1. But 3/4 times 5/7, well, that's just up there. But the 7 over 5 times 5 over 7 is equal to 1. That's our rule there. This fraction times this fraction is 1. And so the whole thing simplifies because once you have a 1 on the bottom, it's just the numerator. So you just get 3 over 4 times 5 over 7. So to summarize, we've replaced the division by 7 over 5 with a multiplication by 5 over 7. And if you go back to the examples that we did of division on the previous slides, you'll see that that works for all of those examples too. Whenever we were dividing by a fraction, we could have gotten that answer just by multiplying instead by the reciprocal. And so here's the general rule that makes division of fractions pretty simple. A over B divided by C over D equals A over B times D over C. This one is the reciprocal of that one. Or in words, to divide by a fraction, multiply by the reciprocal. So for example, if we have 3 over 5 divided by a half, that's the same as 3 over 5 times the reciprocal 2 over 1. And we know how to multiply fractions. Product of the numerators, product of the denominators, the result is 6 over 5. Another example, written in this alternate way of writing division. 4 over 7 divided by 3 over 11. There's 4 over 7, and we're multiplying by the reciprocal of the denominator, multiplying by 11 over 3 instead of 3 over 11. Then the multiplication is easy. 4 times 11 is 44. 7 times 3 is 21. So 4 over 7 divided by 3 over 11 is 44 over 21. Which is just a little bit more than 2, isn't it? A bit more than 2. It's telling us if we have 4 over 7 and we want to ask how many 3/11ths fit inside 4 7ths, the answer is just a little bit more than 2. It's 44 over 21 of these. Well done, students. If you've been able to follow this revision, we've packed a lot of material into the last 2 lectures. A lot of material, a complete review of fractions and where they fit on the number line, and how we add, subtract, multiply, and divide with fractions. Very important topic for Year 9 students to have under your belt. Okay, so now you will want to practice. Please have a go at putting pen to paper and doing some practice, always without a calculator, please. Alright, so we have 3 questions here. The first is to calculate some additions and subtractions involving fractions. And then the next one is to simplify various expressions. And we have some mixtures of multiplications and divisions and additions and subtractions. Something like this, I remind you, means 2 over 3 times 1 over 4. So you have to calculate that first. And then you have to add the result of calculating 1/2 divided by 1/4. So you have to separately calculate this, and then sum them up. And the third question is to verify some of our laws of arithmetic, which don't just hold for integers, but they also hold for fractions. Okay. So here, for example, is the associative law of addition. There's 3 fractions, and I'm saying, well, if you add these 2 first and then add the third one, that's the same as adding the first one to the sum of the second and third. But when you calculate this, it's quite different from calculating this, because you have to calculate the sum of these 2 first, and then whatever you get from this one, you have to add it to 1/4. Well, over here, you're going to have to make this calculation first, and then take 4/3 and add it to that. Hopefully, you will get the same number in both cases. That's a check for you to see if you've done the arithmetic correctly. Okay, if you get the same numbers for the left side and the right side, then your arithmetic is probably good. If you don't get the same numbers, then you need to go back and check your arithmetic. Here's the same kind of thing with the associative law for multiplication, which also holds for fractions. These 2 fractions multiplied together times this third one is the same as the 8/7 times the product of 1/4 and 3/5 in that order. And here's an example of the distributive law, which again holds for fractions. 4/3 times 1/2 plus 2/5. And notice I haven't put a time sign there. So if there's no time sign, it means multiplication. So 4/3 times whatever you get when you add these two should be equal to 4/3 times 1/2 plus 4/3 times 2/5. And you can practice these laws by just replacing these fractions with fractions of your own choosing. You can make some bigger fractions, and that will give you a good chance to practice your arithmetic with fractions. And the answers to questions 1 and 2 are somewhere over here, hopefully, if I haven't made any mistakes. So well done. We've done a lot of review here, very important stuff. There's still one more aspect of arithmetic that we need to get firmly in our view before we can start the Year 9 proper. And that is arithmetic with decimal numbers, which connects pretty closely to arithmetic with fractions, but it is quite different, and it has sort of different applications. All right. So next time we're going to have a review of arithmetic with decimals. Also very important for Year 9 students. So I hope you'll join me for that. I'm Norman Wildberger, and we'll see you next time.